There we go. Come on. There we go. All right, good morning. I'm going to do more thermochemistry today. We're going to be looking at actually calculating these values that we talked about last time. Remember, we talked about delta H, we talked about Q. Those both represent heat, right? But we're going to see that Q is more of an experimental quantity, so just a quantity of heat, but delta H is more something that we can apply, take this information that we get, one delta H value, and we can use it in many calculations. So delta H is a more kind of transferable term, I would say, than Q is. Q is just a number we get from an experiment, or it's a data point. But delta H is something we can actually use when talking about reactions. So let's get to it. So if we want to think about calculating Q, remember Q is heat energy. Again, this will be a data point. We have two ways of doing it. We can do this sort of thing at constant pressure, which will be what we call coffee cup calorimetry. Or our second option is constant volume, which is called bomb calorimetry. And we're going to look at both of these as ways of allowing us to calculate Q for something, for a given transformation. But in order to do that, we need to first understand a few things about heat transfer. So the way that heat transfers, we already discussed that it goes kind of from hot to cold, right? Heat will go from the source that has more heat to the source that has less heat. And one of those will be the system, one of those will be the surroundings, right? So if we kind of think about the coffee cup calorimetry, let's take a look at what that is. A coffee cup calorimeter is... it's a styrofoam cup. Often it's two styrofoam cups, just for more insulation. That I just put inside each other, or we might just use one. Just depends. What's inside that is a solution. And if we remember that in chemistry, most of the solution is water, by and large. The biggest component by far in any solution that we talk about in Gen Chem is going to be water. So really this is talking about water. And then we've got like a thermometer and stuff. So we've got the thermometer in there. And that's what this looks like. So it's just a styrofoam cup full of water with a thermometer in it. Although technically the water has other things in it, right? Something that is going to be reacting. And so that water, the solution, is really a mixture of solutions of our reactants. So we may have some small amount of, say we're doing this reaction. Let's say we're going to mix hydrochloric acid and sodium hydroxide solutions. If we say we're going to add these two, we would see that our kind of total volume of our solution i.e. water, is about 100 mLs. Right? If we put 50 of each solution together, we should have a total volume of roughly 100. We would see that this would probably be a little bit more than that because this would produce a lot of heat and that would cause the water to expand very slightly. But we don't need to worry about that. We're going to assume that the volumes are additive. So we just add the volume, and we consider the amount of water produced in the reaction also negligible. So when we do this, just consider your volumes that you're adding in to be your total volume. That's it. Don't worry about anything else. We also assume a density of 1 gram per ml, which means that the total volume is equal to the same number in grams. Remember, density converts between mass and volume. 1 gram per mil. So because it's a conversion factor of 1, that means 100 mLs for this problem would be 100 grams. All right, so really what we're considering is this system here, whatever heat is given off of this system is going to be completely absorbed by the surroundings. I'm going to write that out. Whatever heat is consumed or produced in this reaction whatever heat or is consumed or produced is the opposite for the surroundings. And since this reaction is taking place in solution, the surroundings is just that solution. So the system is the reactants. The surroundings would be the water. And technically the coffee cups and the thermometer, but those we just kind of ignore them. They don't really change anything for us. So again, really the surroundings is the entire solution, but since most of that solution is water, we're going to approximate that all the heat that comes out of this reaction goes into the water, if this is an exothermic reaction, which it is. If this was an endothermic reaction, all the heat that's necessary for this reaction to happen would come from the water. So remember that there's always that kind of give and take. So if the system needs energy, it takes it from the surroundings. If the system has extra energy, it gives it to the surroundings. So there's always this kind of equalizing happening here. Mathematically, we can write this as the following. Oops, forgot the very important thing there. So remember that the sign of Q tells us which way the heat is going, right? And whatever we may have for our solution, if it's gaining energy or losing energy, it's the opposite for the system, right? The system and the solution have opposite signs. Again, the sign just tells us which way the energy is going. So this would be the system, the solution, the reaction system. Same thing here. The Q of the system is the opposite of the Q of the surroundings. So whatever heat is gained by the system is lost by the surroundings. Whatever heat is lost by the system is gained by the surroundings. Always opposites of each other. So all of this goes into showing us how we can calculate Q for a reaction. All right, that's what we're looking for here. But we can't measure a reaction directly. We can only measure the surroundings, right? This thermometer has no way of measuring the temperature of hydrochloric acid and sodium hydroxide molecules. Like, those are kind of spread throughout the solution, right? But we can measure the surroundings. Surroundings can be measured pretty easily with a thermometer. By checking the temperature of the water, we can see if the water is heating up and by how much, or if it's cooling down and by how much. So by doing that, we can relate Q to temperature changes. And this will be our kind of first formula of the day. That the Q of a solution, or any whatever you're looking at, could be a substance, but since we're mostly dealing with solution chemistry, we'll talk about it in terms of solutions. It's your MCAT. I call it the MCAT formula because look how similar it is. So we're going to see that there are three factors that play into figuring out the Q for a given solution. Although, again, this could be for a substance. So if you have a piece of metal that you're heating up or whatever, this equation would still work. But I'm just saying right now Q solution so that we can see how it fits into Q reaction later on. This here, M, is either your mass or your moles. Just depends what you're looking at. So it really just means the amount of your solution. Again, because of the solution being mostly water, we say that it's just the amount of water. Again, this simplifies the calculations for us. And these assumptions that we make are pretty valid. They don't really change. So just assuming that the solution is water, density of 1, and all that stuff, it's all okay to do. Experimentally, it's cool. These assumptions don't really change our answers very significantly. Delta T, I'll explain next, will be the change in temperature. Of your solution. And remember that delta will always be your final state of whatever you're looking at. So final temperature minus your initial temperature. I'll write that out. So whatever you start with, whatever you end with. That's what we're looking at here. And then the last bit here is C, which can come in two flavors. You got C sub M and C sub S. They are both useful. They just use different units. They tell us the same thing, they use different units. This one is called the molar heat capacity. And this one, honestly, is less used. CS is much more commonly used in general chemistry. But it would be the it would be something with units of joule per mole times Kelvin, or joules per mole degrees Celsius. Either way. You'll have some sort of units there. This is something that's not used, but it tells you how much energy is needed to change 1 mole of a substance by 1 degree. Basically. Remember we talked about how calories were defined as the amount of energy to raise water's temperature by 1 degree, 1 gram of water. This is the same idea, but it's a mole instead of a gram. So that's the molar heat capacity. This one is the specific heat capacity. And this is the same idea, but it uses mass terms instead. So this one you'll have units of joules per gram degrees Celsius or joules per gram Kelvin. Either way. These would be the units you would have for a specific heat capacity. Which, by the way, notice multiple units, that means it's a conversion factor. But most students tend to just use this as a formula. That's fine. Go right ahead. Notice that with M being mass or moles, the one you'd use would depend on which C you have. If you have Cm, the molar heat capacity, you will use moles where your M is. So you would use Cm if you are given moles. If you are given mass, you'll use Cs, because mass would be in grams, right? So by looking at the units of your heat capacity, whichever one it is, you're either dealing with moles or with grams. Grams is quite 95% of the time, so much more common. All right, so looking at this formula, we can see how we can relate the amount of heat energy to the amount of substance being heated, the temperature change, and then this idea of specific heat capacity, which is how much energy it takes to increase the temperature of your substance. And we're going to see that this is different. Some substances, it's really easy to heat them up. Most metals are really easy to heat up. They don't need a lot of energy to increase their temperature. And so they have low specific heat capacities. Things like water, on the other hand, have very high specific heat capacities, and they take a lot of energy to heat up. And so this becomes important when you're looking at something like designing engine coolant. You want something with a high specific heat capacity because it can take a lot of heat energy before it increases its temperature. If you choose something that has low heat energy or low specific heat capacity, every time it absorbs just a little bit of energy, it starts heating up really quickly. So with coolants, you want them to stay lower temperature, right? So they absorb more energy. So there are still like physical reasons you would choose certain things to be your coolant. So you use water and ethylene glycol, right? Typically, for any of you who know cars. You use those as engine coolant because they have very high specific heat capacity. So they can absorb a lot of heat before changing their temperature. So I'll just write that down here. I am totally out of colors. Where's that like forest green? Yeah, there we go. Heat capacity is how much energy it takes to raise a certain amount of whatever substance by 1 degree Celsius or 1 Kelvin. So that's what heat capacity means. So in words, it's how much energy is required to raise the temperature of a certain amount of substance by 1 degree Celsius or Kelvin. This is different for every substance. So water as a liquid has one about 4.184. Water as a gas, I don't know, but it's going to be less. Ice would be less than waters as a liquid. Here, let's look at some common specific heat capacities. Let's see. We've got some. So air has a heat capacity of about 1. Let's see. Here we go. Oh, look at all these. Human tissue has a heat capacity of about 3.5 joules per gram Kelvin. Arsenic 0.3, so arsenic is quite low. Gold 0.129, very small. Hydrogen gas 14.3. That would be an excellent coolant, except that hydrogen is flammable, right? So probably not a good idea. Many gases are around 1, though. We'll see. So water is about 4.184. As steam, it's about 2. As ice, it's about 2 as well. I'll just put this here. I'll put this in Discord, a table of specific heat capacities. just so we have that, I'll put it in our extra resources, just so y'all can see. So just so you have an idea of what these numbers look like. We're looking at that first column. But this table also gives us... actually, why am I not just showing it? It also shows us molar heat capacities. So these are just at different units, right? So joules per gram Kelvin or joules per mole Kelvin. And so I was looking at these, the mass heat capacity, so the specific heat capacity. And we see here there's quite a variety. So liquid ammonia, 4.7, argon, 0.52, bismuth, 0.123, so very, very low. Typically, the heavy metals tend to have very low ones, like lead, like gold, really low. Gases tend to be a little bit higher. And these are also somewhat related to their conductivity. Gases tend to be insulators. Water is an insulator. But these metals tend to be conductors as well. There's a loose correlation there. So just for your information, these vary. So apparently hydrogen is probably the biggest at about 14.3, and the lowest I saw was about 0.12. So, no, 0.116 for uranium. So, yeah, so they vary quite a bit. So the point is they vary from substance to substance. But for water, when you'll want to know, so CS, the specific heat capacity of water as a liquid, the most common one we're going to use is 4.184 joules per gram degree Celsius, or 4.184 joules per gram Kelvin. They're the same. Those units are interchangeable. Why is that? Well, remember in our formula, here's an asterisk. Note a change of 1 degree Celsius is equal to 1 Kelvin. But you'll be like, well, hold up. We just did all this 273.15 business, adding that to Celsius to get Kelvin. That's true for one number. But when you're doing a change in, remember that delta T is your final temperature minus your initial temperature. Let's say we have 10 degrees Celsius and 0 degrees Celsius. The delta T would be 10 minus 0, which is 10. Ignoring sig figs for now because I'm just showing you. If we convert both of these to Kelvin, delta T would be 283.15 minus 273.15, which is, lo and behold, 10. So you are free to use Kelvin. I don't think that's a good idea, though, because it's just adding extra work for you. But if you want to use Kelvin temperatures, make sure you change them before you do your delta T. Change your actual temperatures, not the delta T. If you were to say delta T, oh, well, that's just really 10 plus 273, which is 283, that's a no-no. Delta T is not going to be... You can't just take delta T and convert it to Kelvin. You can only take regular temperatures and convert those to Kelvin. So if you want to convert all the TF and the TI to Kelvin, go right ahead, but you're going to get the same answer if you use them as Celsius. So, because we're looking at a change in temperature. And to go from Celsius to Kelvin, we just add 273. Right? So, it's really... if we have this, like if we were to convert them each to Kelvin, we're just doing 273.15 minus 273.15. So that just cancels itself out. So the point is this: a change of 1 degree Celsius is the same as a change of 1 Kelvin. So delta T for Celsius is equal to delta T in Kelvin. That's why these units are interchangeable here. So whichever one you're given, if you're given joules per gram degree Celsius, it's the same thing as joules per gram Kelvin. Those are the same units for specific heat capacity. All right, so that's the idea here. So just keep that in mind. Let's go ahead and actually do something with this. So we have our specific heat capacity of water. Let's just look at an example. Let's say I want to raise of water from 25 to 100. What heat do I need? Remember, for water, and for nothing else, grams and milliliters are interchangeable. So this really means, because the density is 1, 500 grams of water. Remembering that the specific heat capacity for liquid water is 4.184 joules per gram Kelvin, or gram degree Celsius, whichever one, doesn't matter. We can figure this out. The question is asking how much heat. How much heat is Q? Q is heat. Remember that our formula MC delta T. We have to look at this question and figure out what parts correspond with what. So with M, we're looking for mass or moles, right? Since our specific heat capacity is given with units of grams, we're probably looking for grams. So that tells us that this number here is our M. Our specific heat capacities are given to us, so we're good there. And so we just need to figure out what's our delta T. And shame on me, I have not done my sig figs properly, so poof, there we go, now 100 degrees Celsius. So if we want to analyze those, one of these is the initial, one's the final. How do we know? Well, we look at the language, right? It says from 25 to 100. That language tells us that this is our initial temperature and this is our final temperature. Right? We're starting at 25, we're going to 100. So we have now all of the three components we need. We have M, we have C, and we have delta T. So by doing this, we have 500 grams, 4.184 joules per gram Kelvin. Or I can say degrees Celsius because that's the units I've been given. Remember, those are interchangeable here. Interchangeable units. And then we need our delta T, which will be T final minus T initial, which will be 100 degrees Celsius minus 25 degrees Celsius. Mathematically speaking, of course, this is 75 degrees Celsius, with correct sig figs, of course. And so we'll go ahead and just multiply it out. Notice, by the way, let's check our units. Grams cancel out. Degrees Celsius will cancel out. And we'll be left with joules, which is a unit of energy, right? Where's my calculator? Here it is. Ta-da, let's do it. All right, I'm going to boil my 2 cups of water. That's about 500 mLs. So 500 times 4.184 times 75. And I get 156,900 joules. Quite a bit of energy, right? A joule is not very much, so we might say kilojoules instead. So with proper sig figs, it looks like we have 3 sig figs, 4 sig figs, 2 sig figs. So our answer should have 2, which therefore will round to 160,000 joules or 160 kilojoules. Either way, we're good. 1.6 times 10 to the 5th joules, whatever, it all works. Often, though, kilojoules is a pretty common unit for chemistry, so I would be familiar with that. Again, going from base unit to kilo, we're almost halfway through the semester. Maybe we're halfway through the semester. Should be easy to do. Kilo, milli, all these should be pretty standard by now. Okay? So, in this case, it's going to take about 160,000 joules for us to heat up this water. All right, quite a bit of energy, right? So that's how we'll use this formula. Just like any other formula, of course, you can be given any combination of these things, and I can ask you to calculate one of them. I could ask you to calculate the specific heat capacity if I give you Qm and delta T. If I give you QC and delta T, I can have you calculate M, or whatever it is, right? I can ask you any of these things. Let's even see. Okay, if it takes 122 kilojoules of energy to heat my... How much coffee should I have? I'll have a liter. I'm going to say, because it's mostly water, we're going to, again, assume our density is 1. So we're okay. Here's another one. So not in the context of reactions, just using this idea of specific heat capacity. Next, we're going to put it in terms of reactions. So just bear with me. I still want to get us used to using this formula to calculate Q, and then we'll put it in context of these calorimeters that we talked about. All right. So let's go ahead and look at this question and see what these numbers correspond with. So if we just go through, the first question we see is 122 kilojoules. If we don't know what that means, look for words around it. It says of energy. So that tells us that's Q. We could also tell it's Q by the unit, joules, right? Q has the unit of joules. Next number we have is 1000 ml, and we're given the density. Remember that for water, milliliters and grams are equivalent because the density is 1. Maybe later we'll do one where the density is not 1, but for right now, grams and milliliters are equivalent. So we can say this is grams, which means that this is our M, our mass here. Oops. And then the last number we have here is 100 degrees Celsius. If we don't know what that number represents, we can read the question and we see, oh, we're heating it to 100 degrees Celsius. That tells us that this is the final temperature. We could also understand that because the question is asking it what temperature is the coffee initially, of course what we're finding is Ti. That's what we're finding in this problem. And so therefore the other one must be the TF, right? I typically will not give you extra information that's not necessary. So, and then of course the specific heat capacity is going to be the same because we're still using water as our thing here. Okay, we assume that all solutions have a Q of 4.184 because they're mostly water. Okay, so with that, if we look at our equation, and if I rewrite this, with any equation, we can either plug stuff in and then solve for our variable, or we can solve for our variable first and then plug stuff in. I like the second way, but do whatever way you like. If you are the person who wants to plug in the numbers and then solve for Ti, it doesn't matter. Mathematically, you'll get the same answer. However, I'm going to do it a little bit differently. So if I have that, if I want to solve this equation for Ti, I can get Q over MC equals TF minus Ti. If I solve for Ti, I will get, let's see, it'll be TF minus Q over MC. That will be how I would have solved this equation for Ti, right? You'd add Ti to both sides, or subtract TF and then multiply everything by -1, whichever way. Solve it, algebra, not too bad. Solving an equation for a variable. Again, if you want, plug your numbers in first and then solve for the variable, go right ahead. Not going to stop you. But this will tell us. So if we go ahead and use this, our initial temperature will be our final temperature minus Q, which is 122 kilojoules. Note that because our specific heat capacity is in joules, we need to convert this number. So that's just that many joules, right? Kilojoules is 1,000, right? So we need to add 1,000 to that. So 122,000 joules over our mass, which was 1,000 grams, and our specific heat capacity. Notice grams and joules will cancel out. We'll be left with degrees Celsius. Technically 1 over degrees Celsius, which is degrees Celsius. Let's do the math. So here we go. 100 minus 122,000 divided by 1,000 divided by 4.184. Lo and behold, my coffee was at 70.8 for whatever degrees Celsius. With this, it looks like we need to have our number end with the ones place by subtraction rules. So this should be 71, I guess. I'll need to round up degrees Celsius. All right, again, never mind that none of these numbers are 2 sig figs. When we're doing subtraction, we don't care about the number of sig figs. We care about where that sig figs is. Wow, that's terrible grammar. Where those sig figs are. If we, just accept it, I suppose. This is the ones place, right? This is the ones place. So we need our answer to have the same thing. Whatever we get on the other side will be more significant, but fine, I'll actually do it. All right. Y'all never going to believe me. 122,000 divided by 1,000 divided by 4.184 numerically speaking, this thing is 29.1586, whatever, 9991. We would need 3 sig figs here, right? Which would tell us that the 0.1, the 10th place, is significant. And so if we do 100 minus this number, we have our arrows. We're going to end there. So really 70.841. We end up rounding everything on the left side. This rounds up to 71. Don't forget your sig figs. So, but in class, just trust me, I'll get them for you. But don't forget on your homework to always use the appropriate sig figs. All right, so that is our answer here. So I started at 71 degrees Celsius, and I needed that much heat to get up to 100 to get my coffee back up to boiling temperature so I can scald myself while I'm drinking it. So this is the sort of stuff we can do with this equation. So we're relating energy, temperature, mass, and we use a constant to do that. So those 3 measured quantities, we are combining them using the specific heat capacity to figure out one of the others. All right, so that's all this is. So my advice for you when solving problems like this, if you're having trouble figuring out what numbers represent what variables, look at the units. Units of Q will be in joules, kilojoules, something joules, or calories, I suppose. M will be in grams, or some derivation thereof, or moles. T will be given in degrees Celsius or Kelvin. You have to use words to determine if it's the final or initial temperature. And then C is generally going to be given to you unless you're calculating it. So C would be written, the specific heat capacity is blah, blah, blah. So keep those in mind. All right. Any questions so far on this fun stuff? I have some, I wanted to do one with an equation now. Okay. Alrighty. So, here we go. We're going to do it. Now let's actually take a look at something using these calorimeters. So, I'm going to use a problem from the book. We're going to say that 50 mLs of 1 molar NaOH and 50 mLs of 1 molar HCl are combined in a coffee cup calorimeter. So, just showing us, like, the coffee cup calorimeter, we're going to see that this is the one we're going to calculate Q solution for, if that makes sense. We're going to see that we're going to use a different equation for a bomb calorimeter. The temperature increases from 21 degrees Celsius to, let me get the actual number here, 27.5. What's the enthalpy change for this this reaction? Interesting question, is it not? So, what the heck are we going to do here? We need to remember that last time we talked about delta H for a reaction is related to the Q for a reaction, right? But this is kind of, I'm going to erase this. We're going to say delta H is Q for a reaction. So the change in enthalpy for a given process or reaction will be equal to the heat of the reaction at constant pressure. Coffee cup calorimeter means constant pressure. So we need to just remember this. And we remember that we have a couple more things here. Remember that we have the Q of a reaction is the opposite of the Q solution. And then we also know that the Q of the solution we can solve using our MCAT formula. As always with this, since these are aqueous conditions, we are assuming density of 1. We are assuming that we're not losing any heat. We're assuming that our specific heat capacity for the solution is the same for water. All of these assumptions still are going to come into play here. So we're going to see that we can figure out that Q reaction would just be the negative of MC delta T, right? MC delta T tells us about the solution. The opposite of the solution is the reaction, the opposite sign. So we can use this. We can just put a negative sign on it. Now we're talking about Q for the reaction. So it just again tells us which direction things are going. We can solve this in a number of ways, right? And we're going to see that we can have one more little bit here that we're going to talk about because delta H is an intensive property. We'll talk about that later. Okay, so but the delta H for this particular process we can calculate right now. So let's see it. Well, the M we don't know right away. We know specific heat capacity. We do know our delta T. Right, this is our final temperature. This is our initial temperature. Aha, but how do we know what the M is going to be here? We talked about this at the beginning. We have two volumes being added together here. And so, therefore, the total volume is 100 ml. And so therefore the mass is approximately 100 grams. Because again, because this is water, water's density is 1, meaning that milliliters and grams are the same for water and only for water. But that makes it easy for us, right? Otherwise I'd have to give you masses or densities or something else. So our mass is 100 grams here. So that's our mass. And so delta T would be 27.5 minus 21, which is 6.5 degrees Celsius. So we have all of our numbers here. So let's go through it. It will be negative 100 grams. C, 4.184 joules per gram degrees Celsius, 6.5 degrees Celsius. Notice that the 6.5 degrees Celsius is with correct sig figs. This has only 2 sig figs. This is 4, this is 4. So our answer is going to have 2 sig figs. Even though none of the numbers here had 2 sig figs, it all is about what we're actually using number-wise to calculate. We're using 6.5 to multiply. So our answer is still going to have 2 sig figs. All right, here we go. All right, let's do this. 100 times 4.184 times 6.5. Negative 2719.6 joules. Remember, we have two sig figs here. Just so we know our grams and degrees Celsius cancel out, we're left with joules, which is what we should have for Q. And so this number represents the amount of reactants that we put in for these particular amounts of reactants. And so that's our Q. We have calculated it. Negative Q means this is an exothermic reaction. We're producing heat, which means our surroundings increased in temperature. So remember, negative Q for a reaction tells us it's exothermic. So, but this number tells us the amount of energy for these particular reactants. If we do this, if we understand that what this means that negative 2,719.6 joules, again not rounded yet, is for 0.0 is for that many moles of NaOH or HCl. How did I get that number? Moles is your liters times your molarity. So 0.05 liters, which is what 50 mLs is, times 1 molar, gives us 0.05 moles. So this number represents the amount of energy that was released. Yeah. So why is it negative? Because Q solution is the positive one. That's the one we're looking at. We have the numbers for the solution. But since we're interested in the reaction, remember that the sign is always opposite for your surroundings versus your system. So if our solution, which is the surroundings, had the positive version of the formula, our reaction is going to have the opposite sign, the negative of this. If you wanted, you could have solved it as positive first. That gives you Q solution. And then you would need to use this formula. So I had just combined these two equations into this one, substituted in Q solution for both of these. So Q reaction is negative Q solution, because the surroundings and system are opposite of each other. If Q solution is MC delta T, then negative Q solution is negative MC delta T. That's where the negative comes from. Yep. Okie dokie. Cool. So this number gave us the amount of energy for 0.05 moles of our reactants. But we're going to see that we're going to want this to kind of be more standardized. So we usually report delta H for 1 mole of your reactant. So if we have this value for 0.05 moles, we can say that, well, it should be just kind of proportionally the same number for 1 mole, right? If 0.05 moles gave us negative 2,700 joules, well, 10 times that many moles should give us 10 times that energy, right? Or 20 times that moles should give us 20 times that amount of energy. And so it's really a proportion. So we see that negative 2719.6 joules is for 0.05 moles. We could see what that is for 1 mole, proportion-wise. And thankfully, since it's 1, we can just do this directly. If we take our joules here and divide them by the moles, we're going to end up with delta H, which we often report in joules per mole or kilojoules per mole. So if we do this, so negative 2719.6 divided by 0.05, we get X equals 54,392, negative joules per mole. And this number here is our delta H for the reaction, because we want to describe it for 1 mole. Here we calculated it and we had 0.05 moles of our reactants. We were able to calculate this number, but proportionally that number would be the same, or the proportion would be the same if we had more moles or less moles. We would still have the same ratio of energy to moles. And so if we were to round this, by the way, that ends up being 54,000 joules per mole, negative, or negative 54 kilojoules per mole for this reaction. Either way. This is delta H reaction. Delta H for a process, it's units of joules or kilojoules. Delta H for a reaction is units of kilojoules per mole. So all you need to do is divide your Q, whatever you calculate, divide by the moles that you used in your reaction. So delta H itself, without a subscript, is Q reaction. But if we want delta H reaction, we want it per mole. It's a standard way of talking about it. So this is for a given set of conditions for 1 mole of the substance. So that's the difference here. Delta H reaction is something we can compare because it's standardized to 1 mole. Delta H without a subscript is for whatever happen to be going on in your conditions. So for your 50 mLs of this, 50 mLs of that, for those conditions, you get a delta H out. This is a standard one. This is a standardized measure of the same thing. So by calculating delta H, we can standardize it by dividing by the moles we used in our reaction. And we can therefore get something that we can compare things with. So we can compare 2 reactions and be like, well, this reaction is negative 214 kilojoules per mole. This reaction is negative 54 kilojoules per mole. And so we can say, well, the first one is much more exothermic than this one is. So in order to compare reactions to each other, we need to have them standardized. So we standardize it by taking your Q reaction and dividing it by the moles that you used in your reaction. So do we see this distinction here? So delta H by itself is just a measurement. It's something that we have figured out using our calorimeter, and we figured out the Q of the reaction, which is our delta H. That's the change in heat energy from reactants to products. However, if we want to standardize it, we make it so that amount, we report the amount of energy that it would be for 1 mole. Delta H is whatever amount of energy for however many moles, because you're just doing it for your particular reaction. But now we standardize it by dividing by our moles. Okay? I said that like 5 times, so I hope it makes sense. So that's what we would do here. Okay. Fun. Any questions on this? If we want to put it all at once, I'm just going to get rid of that actually. If I want to standardize this into a new formula, your delta H for a reaction is your negative MCAT, that's Q reaction, over your moles that you're reacting. And so often it's reported as what's the best way to describe this? For 1 mole of whichever reactant you're looking at. So in this case, it didn't matter because the coefficients were all 1. But I might ask you specifically for moles of one particular reactant. And that's not something we'll worry about really here. It just tells you which one to use. In this case, both of our moles were 0.05. I could have chosen to frame my delta H in terms of moles of NaOH or moles of HCl. They're the same. It doesn't matter. But in a question, I might ask you, like, what's this delta H in terms of kilojoules per mole NaOH? And so you would use the moles of NaOH here. So moles of, here would be moles of whichever reactant is specified. So if it matters. So, because sometimes different coefficients come into play, so typically that'll be in terms of reactant, whichever reactant is specified. So, again, this case it didn't matter because they had the same moles. We'll see later, sometimes it does matter. Alrighty. So this is for coffee cup, aka constant pressure. All right, let's look at the bomb. So there are plenty of problems on your homework about delta H reaction. Just remember that this number, the moles, we can get it from grams using the molar mass, or we can get it from the volume by using the molarity. In this case, because we had the solutions, we used the volume to find with the molarity to figure out what the moles were. Sometimes you'll be giving grams. So say I'm adding 5 grams of sodium hydroxide doing this reaction. You remember you can figure out moles from grams as well. So it just depends what you're looking at. Okay? So there are homework problems on that. There are more in the book. I would suggest you look at those. There is some thermochemistry practice, I hope, on Canvas. I haven't actually checked this semester if it's still functional. Let's take a look. I'm on the wrong course. There should be a thermochemistry practice towards the bottom of Canvas. I'm going to just check if this is still a valid link. File not found. Of course not. All right, I've got to find more help for you guys, but we'll get to that later. Okay. Awesome. Okay, so I will find you more practice because unfortunately, just time-wise, I would love to do more, but we must go forward. So a bomb calorimeter, speaking of moving forward, is a little bit different. So this is constant volume. And constant volume calorimetry, different. It's got a box. The box is the bomb. So this is a very rigid container that is kind of designed to withstand high pressure. So it's a very important piece of equipment because it's going to keep the volume the same. So again, no work is being done here because volume is the same. No pressure volume work. With this, you have thermometer. You have your water around it. Inside that water, or rather, you have a kind of like a reaction vessel. Often this is done for burning things. So if you want to find out the caloric value of your Cheez-Its, this number up here, the 210 calories, that's done using a bomb calorimeter. So what happens is you have this kind of reaction vessel. And you put your sample in, your Cheez-Its, you put those in that reaction vessel. There's also a tube that puts in pure oxygen, and you have little wires in there to ignite it. So you heat up your sample, you ignite it, and you burn it and figure out how much energy comes out. So what happens with this is all of this is kind of accounted for when designing a bomb calorimeter. We're going to see that. Let me just see if I've drawn everything that I need to draw on these things. Yeah, we're good. We're going to see that thankfully all of this stuff is included in our. We don't have to do MCAT for this because we have a fixed volume of water. We have a fixed kind of specific heat capacity. And so we're going to see that our Q reaction for a bomb calorimeter is the specific heat of the calorimeter times the delta T. And the specific heat for the calorimeter is something that you would calculate by given other parameters, or it's given to you. So we'll do a few problems here to see. And just like before, delta H equals Q reaction, or delta H reaction equals Q reaction over moles, or delta H reaction, subbing all these things in would be negative C of your calorimeter times delta T over your moles. So any of these will work, right? I'm going to frame it first by using the big equation on the left. So, again, I don't want to make up numbers for these because it'll be hard to compare them then. So I'm going to use a problem from the book. So we're putting in 4 grams of methylhydrazine. That's an organic compound. Gets combusted in this a bomb calorimeter. With a heat capacity of 7.794. kilojoules per degree Celsius. Notice there's no grams for this calorimeter thing because that's already taken care of with CCal. It's incorporating our mass of the calorimeter, incorporates the specific heat of the entire calorimeter. So note the units do not include mass for this. And we don't need the mass because we're just, that mass that we're given here is for our moles. Okay, let's see. The temperature, Let's see what our temperature change is going to be. It increases from 25 degrees Celsius to 39.5. So these calorimeters often have very fancy equipment because you keep using them over and over again. Once you establish your heat capacity of your calorimeter, you can just keep using it. So very fancy thermometers are often used with these because, it would be very problematic if, companies were not reporting their calories correctly, right? Remember that kilojoules and calories they're both units of energy. We can convert between them. So here we go. I need to give you an equation for this because we don't know what methyl hydrazine is in this class. So I'm sorry, we need more hydrogens, of course. Plus oxygen, I think 5 of them, if I remember, yeah. We don't really need to know this. We get CO2 and water, I assume, yeah. How much CO2? I don't want to balance this. All right, fun stuff. So if we want to find our Q, we don't actually need this equation. We have enough information just given here in the problem to find Q. Remember that Q for a bomb is your calorimeter heat capacity times delta T. So negative 7.794 kilojoules per degree Celsius times 39.50 minus 25. Let's do the math here. This is 14.50. Both of these numbers will have 4 sig figs, so that's good for us. We don't have to think. 7.794 times 14.5. And we get negative 113.013 kilojoules. Degrees Celsius cancels out. We're already left with kilojoules because our calorimeters units are kilojoules already. So degrees Celsius cancels out. Left with kilojoules. That's our Q reaction. But remember that delta H reaction is Q reaction over the moles of reactant. And so, is there any way we can get moles of reactant here? Well, we've used this number. This was our C-cal. This was our temperature initial. This is our temperature final. Aha, but we have this number we haven't used. So indeed, that's one of our reactants. That's that first thing in the reactant, by the way. And so we will want to figure this out in terms of moles, right? So we need to do that. So methyl hydrazine will need its molar mass. Do it. 12.01 plus 6 times 1.008 plus 28.02 is 46.078. Okay, we have our molar mass. So 4 grams, 46.078 grams. 1 mole will give us 4 divided by answer 0.0868093, whatever, moles. Again, I'm not going to round this number yet because we're still going to do stuff with it. So if we want delta H for this reaction, we can plug this in now. Four sig figs on the top, 3 sig figs on the bottom. So our answer is going to have 3 sig figs, which is 113.013 divided by that answer gives us negative 1,301.85 kilojoules per mole, which we need 3 sig figs, negative 1.30 times 10 to the third kilojoules per mole. We did it. Don't forget, for 3 sig figs, we can't do it any other way besides scientific notation, so that is unfortunate. But there we have it. So our final answer for this, if we find the delta H for this reaction for the combustion of methylhydrazine, should be that many kilojoules for 1 mole of methylhydrazine. Or at about 1300 is released. All right, so that is bomb calorimetry. It's really the same idea, just slightly different equation for Q. And so I'm going to just write them all out again. So Q reaction is either negative MC delta T or is negative C calorimeter times delta T. This one is for coffee cup. This one is for the bomb. And so, delta H, remember, for a reaction is Q reaction, whatever it may be, divided by your moles of whatever reactant you're looking at. So we were given methylhydrazine in this case, so we're using methylhydrazine as our moles. The last case we had HCl. We used HCl's moles. So whatever it may be. All right. I want to do one more where I show you how to figure out the first step for using a bomb calorimeter is to standardize it, to figure out C-cal. And so you'll use things that you already know. Or maybe we should just do this. What day is it? Today's Tuesday? Maybe we should just do this Thursday. I don't know. I kind of want to finish this. So, here we go. So, if we know, this is how we'll figure out if you standardize your bomb, standardizing the bomb. Okay. This will be, let's do one of your homework problems. They're here somewhere. Where's bomb calorimetry? Okay. Coffee cup, bomb. This is all telling us the heat capacity. Aha! Okay. Problem 59. We're going to do it. So, let's say we already know heat of combustion is, copying this out of our book, 15.57 grams, kilojoules per gram. All right, so we're going to use 1 gram of glucose. We're going to burn it. We're going to get out 15.57 kilojoules. If 3.5 grams is burned, and the temp increases from 20.94 to 24.72, we can figure out by using something we already know the heat of combustion of. This is delta H in terms of units of kilojoules per gram instead. Just going to make this a little bit easier for us. We can figure out what the C-cal is, right? We know that the Q of the reaction was negative C-cal times delta T, or C-cal is negative Q reaction over delta T. We can solve this, hopefully. The Q of the reaction is going to be the burning of that 3.5 grams. We know that burning 1 gram gives us 15.57 kilojoules. So if we burn 3.5 grams, we would get 3.5 times 15 point whatever, right? So we know that we have 3.5 grams of glucose times our 15.57 kilojoules per gram. Notice that's just a conversion factor. We're just putting those together. We have our delta T, which is 24.72 minus 20.94. All we have to do is do the math. Notice we needed this because the Q, this is the heat of combustion in terms of kilojoules per gram. That's delta H, essentially, right? But in terms of kilojoules per gram. It's not as common to report it this way, but this problem is designed to make it a little easier for you instead of you having to convert to moles first. If it's kilojoules per mole, then you'll put the moles in instead, right? It's just our way of what we did last time. We divided Q by moles to get delta H. If we're given delta H and we need Q, we would multiply delta H times moles, right? But this is delta H in terms of grams, so we're multiplying by grams instead. Anyways, so 3.5 grams times 15.57 divided by 24.72 minus 20.94. 14.41 kilojoules per degree Celsius. Sig fig wise, we're going to probably have 3 sig figs here. So 14.4 kilojoules per degree Celsius. And so that's what we'll have here. So you can end up calculating this if you already know what substance you're burning, if you already have its heat of combustion, its delta H. You can standardize a new calorimeter and find out its heat capacity. And then you can use that calorimeter for other things. Like this is part A of the question. Part B says now you use this calorimeter to burn this unknown or this other substance to figure out what its delta H is going to be. So typically this is a pretty common process. So fun stuff. All right, so practice well, study well, and we'll go forward. We'll keep on talking about thermochemistry. We'll talk about now theoretical ways to get delta H. So this is delta H in experimental ways. So using all these data points, measuring the temperature change, measuring the masses that are used or the volumes that are used. That's all measurement. It's all experimental. And so on Thursday, we'll talk about theoretical ways to figure out delta H. All right, so we'll continue on. All right, have fun. See you guys next time.